We're streaming. We're recording. Good to have you all for yet another coding session. Look, we all love coding sessions. So, but before we get to the coding session, we're rounding out the end of the term. So, folks, if you can make sure that you are, again, what's critical right now are your projects, okay? But I just want to give you a bit of a outline for what's happening for like the rest of the term here. So we've got a new sheet. All right, before I get off to our fun little coding exercises, we'll see how far we get as we get all these. We're kind of rounding out the end of the semester, which is a couple of fun topics, okay? But today, 2026, 04/16, okay? So number one, the TAs right now are hammering out your grading for your homeworks and previous project updates. They're literally working on that as we speak. They've been working hard on that. So I understand homework 2 was sometimes a little bit harder than homework 1, maybe particularly on the grad students. So those are being graded right now. So here's what we have remaining, okay? One, so given the fact we don't have a lot of time for homework 3 left, okay? But I think it would be fun to perhaps do one for recovered credit, okay? So if you get your homework 2 back or homework 1 back and you're like, I need some points back, it'll be great. That's what homework 3 is for. And it'll be due on the Friday of finals week, okay? So I give you a little over 2 weeks to do it. I know you got a lot going on finals week, and senior design hopefully is ending soon for those seniors and things like that. But it's due the Friday of finals week. We'll put the assignment up. But this is a reinforcement learning. Learning homework, okay? All right. And the exact number of points that we would get back, we're still figuring that based upon like how many points people lost in the assignment for homework 2 and homework 1. But the idea is that reinforcement learning homework. But the idea is we're going to take Silly Frog, the example from class, okay, which we solved using value-based methods, value iteration. We want you to solve it using temporal difference learning, okay? Okay? And that can mean using actor critic. Now, to be clear, you do not need to solve it with a neural network, okay? It need not be a neural network. Okay, and you will just submit your code like you would any other assignment, or you can run it, and we'll get the details out soon. But if you want to get cracking, okay, the silly frog the silly frog example is all done using value-based methods, where we iterate on the value of every state on the lily pads, okay, and then you say, wait, what do I do? Well, it's dependent upon what's the highest value, right? Okay, and what I want from you is to be able to solve it where you're using a temporal difference update. And what that means is what you are doing policy iteration. Before you're doing value iteration, now you're doing policy iteration. Okay, you need a temporal difference update for that. Okay, it's not a very complicated problem, but it's an opportunity to get, it'll be worth fewer points you can get, but those are rewarded back to some previous assignment. Okay, there's some way. Basically, if you do this homework, there'll be some way it can help you, but it cannot hurt you. Okay, does that make sense? Now, please make sure it's on your own work, of course. That's what we're doing. So that's what homework 3 is. It's more basically because it's because it cannot hurt you. It's an optional assignment. If you did great at homework 1, homework 2, awesome. You can do this for fun. Why not? Okay, but it's not required. All right, and so that's the only homework remaining. Okay, we're looking at your quizzes as whether or not we do any one last quiz before the end of the term. Again, these are just open book, open note quizzes, no different. See if we do any, if the averages are such that we need to do any more. To make sure people get a chance to make it up. We will see. That's the only question we have left remaining in the air that we get out there. But other than that, you have your project. And that's going to be again, that's the last day of finals. Okay. And and to be clear, we have the update due Monday. Okay. All right. The assignment page is up on the exact time when it's due. It's up on the assignment page. You can check it out. All right. That's due Monday. And that's important because on Thursday, we'll have a project workshop. Okay. We have a project workshop for where unlike every other Thursday, okay, where we are remote, this is your opportunity to meet with all the TAs in person. The TAs will be in class, in person, in the lecture hall room to meet with students to help them with their projects, okay? It's an opportunity to ask them questions like, oh, I'm doing this, I'm running this problem, what do you do? And they will give you advice, okay? You will meet with the TAs, okay? Thursday of next week, 1 week from today, all right? So that way you will have an opportunity to submit your project update by Monday. So the TAs have something to look at for the most recent stuff. Then they can talk to you about it on your project workshop on Thursday, okay, to guide you toward a good solution for your whole project that is due on the last day of finals, okay? That's the roadmap for the end of the term. Any questions about any of that? In 3, 2, 1. Okay. All right. So it's all designed to help you out to make sure you have a good project at the end of the term, right? All right. So a couple topics I wanted to talk about today. Okay. We spent a lot of time doing reinforcement learning. Okay. But we kind of glossed over a little bit of one of the important elements of the reinforcement learning loop. So recall, reinforcement learning. You've got some agent, which has a policy that takes in some state and spits out some action, and some action goes into some environment, E and V. Okay, and that environment will say, hey, here's my state, and we'll also give you a reward, right? Reward R. And one thing we've glossed over a couple of different ways is the environment, because in a way, the environment, it's much bigger than machine learning. It's simulation, or or sometimes not even a simulated environment. Sometimes people will do reinforcement learning on a piece of, in a physical environment, or even getting feedback from people, right? Imagine you have an algorithm and you're having it do something, like let's say it's like a Chat GPT style of algorithm. Question is is it working well, right? One thing you can do is you can ask you can ask the person, is that working well? Thumbs up, thumbs down. There's lots, or any algorithm, or anything that you've written for a website. It's like, did I do a good job? A thumbs up or thumbs down. That can be your reward signal, right? That could be your environment. So it's not even a computer simulation, right? It's literally interacting with a physical environment with people in it, right? Okay. So that's one thing we can do. So anyway, but my point is, you can be a physical environment, but a lot of times in modern reinforcement learning, you need a lot of data for deep reinforcement learning. So we often will simulate this environment. So we want to simulate this environment. So let's talk a little bit more about simulating environments, okay? Okay. Now, some of this will overlap if you've taken any course having to do with dynamic systems. Little skosh of a little bit if you've taken my applied optimal control class. This will overlap a little bit with that. But the idea is that you have some process, okay? You have some function f, okay, that takes some prior state sk and turns it into some next state sk plus 1. This is a discrete time step, meaning it's a physical time step from time step 1 to 2 to 3 to 4 to 5, right? So it operates on a discrete time system. Okay, meaning you have one state, then some period of time passes, then you have another state. Okay, discrete time, that timing is one discrete value, right? As opposed to continuous time, I'm waving my pen around. In physical reality, there aren't these time steps. It's not only caring about from 1 second to the next, where my pen is at. It is smoothly, continuously moving in time. That's continuous time. But when we're dealing with reinforcement learning specifically, we are always dealing with these discrete time systems, or particular snapshots of that system at discrete time points. It can be moving physically around in space, but you're only measuring the state it's in, every once in a while. So it's a discrete time system. So you have some way of mapping where you were before to where you are now through this function that we'll call the dynamics, right? Okay. So imagine you have so if you already have a discrete time system, if someone has already come up with some kind of what is it? Has come up with some kind of computer program that is already a discrete time system that is probably already simulated. So an example might be, chess. Okay, or do checkers. It's easier to draw checkers on a board, right? So you got your checkers. We're gonna have a very small checkerboard. It's only a couple of things wide, all right? But this would be a very boring checker game, right? Where you have that, and you have some, some checkers. They're all in different positions or whatever. Sorry, it's been a while since I played checkers, right? That every time you make a move, that is a time step into the future, right? So each move is a time step. And the way that you simulate checkers is you literally program a game of checkers. All right. And we do a little bit of programming these days in this class. And maybe you can figure out how to program checkers with the amount of Python that you know. Honestly, you probably can. Probably a lot of if statements. You put values into a matrix, and you say, hey, which one do I want to move? And checkers, you go diagonally, right? I've not played checkers in years. I am blanking on checkers. You go diagonally, right? So, and you would say, I want to move piece number 10. Okay. I want to move piece number 10 to the right. Okay, great. I want to move it to the left. Actually, no, it's not allowed. You're too far to the left. It's a bunch of if statements, right? So checkers, each move is a time step. It is discrete time. It's inherently discrete time. Okay, because each move is a time step, right? So, however, for continuous time systems, and that's basically physical systems, like most physical mechanical systems, right? So physical systems need to be approximated in discrete time, right? For the purpose of reinforcement learning. That way, you have one state that goes to the next. Okay, for reinforcement learning. So if you have, let's say you're driving a car. Okay, so you have your car. Look at that car with its little headlights. Car with this back thing, right? Let's say you have that car is in this position right there. You got a question, Jin? Hey, Jin, you have a question? Thanks. All right. Got it. All right. So let's say it has some position x of t, and this is going to move with some equations of motion that says that over time, okay, that this car is going to move. In fact, what we would say is that the derivative of x of t with respect to time is some function of maybe where you're at plus whatever action you take. We'll call it a of t is your action. Okay. This is a continuous time. differential equation, right? And the way you would know how far this is moving from time point to time point is you would solve this differential equation. So simulating systems, dynamical systems, oh, this is a car, by the way. A car. Look at that car. Okay. Simulating dynamical systems is effectively just solving differential equations. Okay. Now you've taken differential equations. You're all mechanical engineers who are upper level mechanical engineers. And we're not talking, though, about solving these analytically by inspection or computing a Wronskian or, you know, whatever methods they teach you in differential equations these days. We're going to solve them numerically, approximately most of the time. So the idea is that you can write the dynamics of any continuous time system, which is governed by ordinary differential equations, to be clear. Okay, we're not talking about some partial differential equations like fluid dynamical equations. Those can get more complicated, but anyway, it's variations on this. Okay, where you have the derivative of some state of your system with respect to the time is equal to some function of your current state and some action you're going to take. This U, that U is an action, okay? In control. All right? This is where it butts up against control systems a little bit, right? Okay? And the way that you solve this equation is actually is pretty simple, okay? At least the way to approximately solve it. There are lots of ways, but this is just your first possible way. So like imagine you, my friends, are trying to come up with a simulation for your system for any purpose, right? If you come up with the equations of motion, these dynamics, right? And you can write them in this form where you have some state and some input, right? You can solve this approximately by saying, hey, what is this derivative? What is that derivative approximately equal to? Well, it's actually approximately equal to the x at some future time delta t minus x of t. This is the rate of change of your state x, okay, over time. So it's over delta t. This is the approximate definition of a derivative, right? If delta t goes to 0 in the limit. That's the definition of a derivative in calculus 1. Okay, but if you don't have an infinitesimally small t, if you just have a small t, this is still approximately true, right? So you'd say it's approximately equal to some function of x of t, u of t, right? Okay, and so if you want to know the state at some future time, delta t, some small change in time, this is called a time step, sometimes called h in some of the literature, often called h. I like calling it delta t because it's pretty obvious, the change in time. All right, you can solve for x of t plus delta t. And if you solve for it, you multiply both sides by delta t, you put x of t on the other side, and then it just becomes x of t plus delta t is approximately equal to x of t plus f of x of t u of t times delta t. All right. And this is called Euler's method. Don't call it Euler's method. I will be offended because, as some of you know, Leonard Euler was my postdoc advisors, PhD advisor. So my grandpa will be upset if you call him Euler instead of Euler. So don't do it. So if you have these equations of motion, which you can get from your from your dynamics class or some advanced dynamics class, or you look them up in a book, right? This is how you would say, hey, this next, you say, my next state is equal to my previous state plus my dynamics times delta t. The example that I give, I'll make it really brief, is let's do a population example, a population growth, like rabbits. Like how do rabbits populations grow over time? Okay. Well, the way you write it out, you say the change in population over time, the rate of change over time is equal to some parameter, okay, alpha times the current population. Now, you could solve this by hand using your differential equations knowledge. You could find out that that's an exponential, right? But the way that you would write this is that if you would solve it numerically, is you would say my initial condition, E of 0, my initial population might be 10 rabbits, right? And if I have some dt is equal to 1 unit of time, I don't know if it's years or months, whatever this equation is scaled to, right? Then that means that P1 is equal to P0 plus this function, which is a function of our state P, okay? So it's alpha times P of t, to be clear that that is this function right there, okay? Times delta t, dt, which is 1, right? So P1 is equal to P0 plus, and by the way, P of t, of course, our current time is 0, so P of 0, so it's alpha P of 0. So whatever alpha is, so it's going to be, so P1 is going to be 1 plus alpha times P0, which is 10, right? And you repeat this for 2, 3, 4, and what you would get is, assuming alpha greater than 0, you're going to get this exponential curve, P of t, with all of these different points on it, right? Each of these are at discrete time points, delta t or dt, whatever I felt like writing, right? We have turned this continuous dynamical system into a series of discrete steps, so now it's time varying. Okay, so now it's discrete time, I'm sorry. All right, so that's how you would take some equations of motion that you would be given for a problem, and then you simulate them, okay? It gets a little bit more complicated when you have more than just one derivative, okay? What you end up doing is you end up having a state vector, called a state vector x, which has multiple states, x1, x2, up to xn, and you have variables where n is the order of your ordinary differential equation, ODE. Okay, that's the trick. So if you have a second order differential equation, such as, here's your example, let's say a spring mass damper system, which is a spring mass system. Here's a spring, here's a mass. I'm going to apply some force to it. We'll call it capital F of t, some force. And there's some position. We'll call S of t, just because we're already going to use x in some other term. The equations for motion of that are m d squared x dt squared is equal to minus k x plus, oh, sorry, s, these are s, I apologize, s squared and minus k s plus f. Okay? And this is a second order differential equation, as you learn the differential equations, because there's two derivatives. It's slightly more complicated than that if you're some weird systems, but this is a good first cut approximation. And you would say that, hey, the number of states I have in my state vector is 2. So I got 2 elements in my state vector, so order 2. There are 2 elements in the state vector. Okay. 2 elements in the state vector. And what are those elements? Well, you start with your lowest order derivative that you have. Your lowest order is s. It's a 0th order derivative. You say my first state is s, and then you say that your second state is d is the next higher derivative, ds dt, until you run out of states. Okay, and this actually works out beautifully, because then you can write dx dt is the derivative of each of those elements. So this is ds dt, ds squared dt squared. And you can see on the right-hand side, this is your function f of your state x of t, right? And then your input u of t. Your input is your input force that you can add. And you say that, hey, ds dt is a state we already have. And ds squared dt squared, we know from this. So we just solve for ds dt squared by dividing both sides by m. Okay, so it's going to be minus k over m times s plus your force that you're applying. So these are now your equations of motion. This is what you use to use Euler's method. That's your F, okay? Okay, those are your dynamics. All right? And that's how you would just, so if you have a system where you have these equations of motion and you want to simulate it, that's the quick and dirty way to simulate these things, okay? My lectures on dynamical systems are available for my Applied Optimal Controls course. The first couple of lectures, you can check them out if you want to get more information, but it's the same idea, okay? That's the really quick version. Talking about this in about 20 minutes, right? So that's helpful because you need to be able to simulate an environment, and your action in this case would be the control input, this force that you apply, that you choose to apply. That would be the action. So in control systems, the action is called U, among other names. There's so many names, but that's your action space, right? So if you want to make an environment from scratch, that's how you make an environment from scratch, okay? As a real quick example, okay, I can pull together this spring mass damper and turn that into some kind of agent. We can go into a new Python notebook. I'm making a new Python notebook right now. Okay. So if you, again, you go to collab.research.google.com. And we're going to speed run the spring mass damper. Okay. Let's where's spring mass damper? There we go. Okay. Spring mass damper. Okay, my friends, I'm going to put the link, make a share link, send this to you all 51 of you in the chat. Okay, share. Like everyone with a link can view. Done. Spring mass damper. Okay. There's the link in the chat. You want to follow along. So we're going to make a quick spring mass damper simulation, okay, by me, Christian Hubicki, and all my friends. All right, and this is like if you've done dynamical systems before, this will be real easy, okay. But if you haven't done it before, you've done simulations before, it's still real easy, okay. Today in the common era, we're going to do a Euler's method simulation of a spring, I guess not even a damper, just a spring mass system. Okay. We're only going to need NumPy and Matplotlib for this. So we're going to say, all right, new plot line of code. So we're going to import NumPy as MP. We're going to alias this as NP. We're going to import matplotlib.pyplot as PLT. Okay, good old-fashioned that. All right, so we're going to simulate our mass damper system. Simulate our mass damper, sorry, our mass spring system. Okay. All right. So we're going to define our parameters. Our mass is going to be equal to, let's say, 1 kilogram. Okay. People see okay. I'm assuming people can see okay. We're doing all right. 1 kilogram. We're going to have our so we're going to have our spring constant. We'll make it 10, and that's going to be in newtons per meter. Those, how you stretch a spring, the force on the spring. Okay, we speed ran through dynamics. You're all mechanical engineers, we're speed running through dynamics, but this is sort of physics 1 stuff. Okay, that when you stretch a linear spring, a Hookean spring, you stretch it by 1 meter. How many newtons of force do you get pushing you back? In this case, we'll do 10 newtons per meter. All right. We also want to define. Our initial state. Now, here's the thing. Let's go back to our our states here. We have 2 states. It was a second order system. Spring mass systems are second order systems because they're governed by the second order differential equations. For those who wonder what this came from, that's F equals ma. I'm speed running here. Speed running F equals ma, right? That's ma. That's your acceleration is equal to the sum of your forces, right? This is your force from your spring pulling you back when you go to the right, pushing you right when you go to the left. And this is some external force that you get to apply, that you get to choose. That is your action, okay? All right, so we define our initial state. We're going to say that our S0, that's our position 0, let's go start it at 1. And our time derivative of S, ds0, we'll call it ds0, is equal to 0. This is your initial position. This is your initial velocity. Bum, 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 bum. Initial velocity. Done. All right. So now we also need a time step for our physics simulation. And we're going to use Euler's method. There are better methods than Euler's method. There's Runge-Kutta methods or RK methods. They're just a little more complicated. In my other class, we covered things like explicit Euler and implicit Euler and trapezoidal and Hermite-Simpson that are implicit methods. That's not important here, okay? But there are better physics simulation methods, all right? Ones where you don't even have to choose the time step. MATLAB and Python have ways, if you have certain types of simulations, it'll choose the time step for you. But for reinforcement learning, we want the time step to be constant. So that way we know that we step forward a certain amount of time, we see the state has changed, okay? So we'll set the time step, we'll call it dt as a time step. We'll make it 0.01 seconds. Okay. What else do we need? So we also want to know for how long. For how long do we want to simulate our system? So like length of time. So time span of simulation. Or actually, you know what? We're gonna do number of time steps. That's very reinforcement learning. That's what we did for our cart pull problem last time. We say, hey, we did the number of time steps. Number of time steps, let's do 100 time steps, okay? All right, so what we can then do is we can say, we can now have a loop where we loop from one time step to the next. We start at time is equal to 0, and then we find out what time is time 0.01. Then we say, hey, now our time 0.01. Use this formula. Find time is equal to 0.02. Rinse and repeat, rinse and repeat, rinse and repeat until you've done it for 100 time steps, right? So we're going to need a loop. We're going to need a loop for that. So we're going to want to store in that loop. Okay, we want to be able to store all of our points of simulation along the way. Okay, so to do that, we're going to want to store our states from the simulation. Okay, in order to do that, we are going to say that we're going to call it our S history, or our S history is going to be equal to is going to be equal to NP dot zeros. We're going to say it's all zeros for starters, okay? And it's going to be n by 1. So it should be 100 states. Is that right? Did that work? Make sure we printed it, just because I might have made a mistake. All right. Oh, I gotta run every. Oh no. Did I undo? Undo. Did I edit? Undo, cell delete. Oh my goodness. Oh. Okay. Whew. Wrong button. Oh, wrong button. Okay. Let's make sure this is working. Let's run all. Run all. So it's already running. Why is it taking so long? Why is it not running? I just want to print something, please. Is not printing? How do I stop? It says it's already running. I'm going to reload. Okay. All right. MP.zeros. Okay. Yeah. So I need that, right? Okay. Is that right? Here we go. Good. All right. So need a tuple n comma 1. All right. Awesome. That's our state history. Now we need our ds history. That's our history of our speeds, our velocities. Okay. np.zeros. We need this for every state. Okay. So stores our states from the simulation. These are our positions. And that's our velocities. Okay. And then we will move forward. Don't worry, we're almost done with this thing. So we're going to do our simulation loop. We're going to use Euler's method. Okay. Then what we're going to say is we're going to say in our first element, S history, the very first one, I believe is going to be, so it's going to be 0. Our very first element is going to be which state? It's going to be S0. And then our ds history, our very first speed, is going to be our very first speed, ds0. S history, ds history, right? Make sure that runs. Good. So now we get to do a for loop. We say for I is in range from 0 through n. We might have to do n minus 1 just because we already have the first element figured out. In fact, we might want to start with 1 since the 0th element has already been added in, right? So what we can do is we get n colon. So what we're going to do is the Euler step. Okay, here's Euler's method. We're going to say that our next time step. So we're going to say S history I, which is the next time step, is equal to S history, the previous time step, t. So history, previous time step, t, I minus 1, plus we have that function here, which we've defined as, for S, our S changes with ds dt. That is our previous speed. So ds history, I minus 1, times delta t, times delta t, dt, times dt. And we're going to say ds history I, so our next one, is equal to our previous one, ds history I minus 1 in the list, the previous one, right? Plus the acceleration. Really, this is what if you think about Euler's method this way, it's saying, hey, our next position is equal to our previous position plus how fast we were going for times how long we were traveling, that speed. That's Euler's method, right? We're applying that for the position, and we're also applying that for the velocity. That's what this all means, okay? So we got to multiply it by our dynamics here, okay, which is given by the dynamics of our second state. So our acceleration is equal to minus k over m plus f. We have not defined f. We'll define f. We'll say f equals 0. So we'll say minus k divided by m times s. So it's be our previous s. So it's s history I minus 1. So our previous time plus f. And we didn't define f. We'll just find f up above. Okay. So f is equal to 0 for now. This is our applied force. Okay. Hopefully you can see that. Applied force is up here. Now we have this step down here. Done. Okay. So now, oh, sorry, N. What is this? What is this? MATLAB. So that's the Euler step loop. Okay. Now we can plot it. We can say plt.plot. Let's just plot the S history and show it. plt.show. Open, close. See what happens. Run all. Okay. Oh, it's a bit of sprungy. Look at it, sprungy. Okay? It's going a little crazy. There's something that's not quite right. I'm pretty sure it's because our time step Needs to be smaller. Here we go. There we go. Now we're talking. All right. So so maybe we do it for fewer time steps. Let's do 50 time steps. I mean, my time step smaller, 0.01, 50 time steps. You can see it's starting to sproing a little bit. See that? Let's make the time step even smaller and make this number bigger. Cancel. There we go. So I made the time step 4 zeros and a 1. I did 500 time steps. Okay. There's a reason sometimes, and that's because Euler, and the reason is that Euler is, you notice this, like it's springing like a spring. You can tell right there. That's good, right? But you'll notice it's gaining energy. That's not a good thing. We're not applying any external forces. And that's because of this approximation here. We are approximating with Euler's method. So if this delta t is not small enough, it can go very wrong. Runge-Kutta methods are better at avoiding this, but it's a way of simulating your system. Okay, so you can always make the time step smaller. Here it's pretty dang small. I'm running it for 500 time steps. There we go. We simulated a system. That's simple, right? Okay. So, and all you need to do is if you have more states, you do this for more steps and you come up with the derivatives of all your states with respect to time and you put them in that term right there. Oh, I forgot to take times delta t. No wonder I screwed up. 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 Okay. All right, let's try n equals 100. I forgot to multiply by delta t in that one line. Let me run this again. All right, we're doing better. We're doing better. Let's make this 1,000 time steps. Just because I'm embarrassed. I forgot to multiply by dt right there. Okay, still same thing. Look, it's going up and down like that. We can make the time step smaller. Let's make it 0.001. That should be more accurate. There we go. My time step is 0.001. I did 1,000 steps. I remember to multiply by dt there. Okay. Yeah, we need more steps. Let's make 10,000 steps on all. There we go. Okay. So yeah, I'm playing around with it, but there's my simulation. There's my spring. Okay. That's how we do it. So that's it for how you simulate a system. You can also use simulation packages that already exist. But I do want to move on to another topic that's a more broad machine learning topic that we haven't talked about yet. And it's an interesting one, okay? All right. And it's the idea of what we call dimensionality reduction, okay? Bit of a hard slam to a different topic, but I want to cover a couple things before the course is over. We're getting to the end of the class now. Okay, so dimensionality reduction. That sounds very opaque. It sounds very abstract. But here's a way to think about it. And this is a method. This is a method of unsupervised learning. Okay. Well, here's the idea. Imagine you have a bunch of data points. Okay. I'm just going to draw data points on some axis, x1 and x2. Okay. A bunch of data points. Okay. Right. That's what they look like. They're kind of scattered around. Okay. This is just data. This is just 2D data. Right. So one thing that it's often useful to do is to take a look at data and try to represent it in a way that captures most of the data, but like not every single point of data. Like get the big picture. What is the big picture that's happening in this data? And one thing to think about it as is that it's kind of like you have this axis is like super important, right? And there's a lot of variance along that axis. And there's like a little bit of variance along this axis. Like I could sort of represent this data as like, well, actually, it's sort of like a bunch of points along this line, along this line, and some points that vary along that line. Kind of looks like a sword the way I drew it, like that kind of weird sword. But anyway, so I took this data that was spread across these two dimensions. And I said, you know what? Between those two dimensions, these two directions were the most important. Okay. One way to think about this is called, principal component analysis, or PCA. Okay. Or PCA. What are the principal components of this data? And so if you had the task of saying, hey, which of these directions, this one or this one, is more important? Is it direction 1 or is it direction 2? Okay. And the answer is probably direction 1, because direction 1 captures so much of the variance in the data that if you were to only look at just this one direction, okay, it would tell you the spread of this data much better. Like, whereas, this direction, all the points are very much collapsed together. There isn't much difference between, this point here and this point here along this axis. But there's a huge difference between this point here and this point there on that axis. So this is what we call, the principal component. And the idea is that if you have a bunch of data and you say, look, this dimension, like, instead of just it being this 2D data, let's say, this is like, this is how much I paid for a product versus how happy I was with it, right? Those two data points, right? I wanted to know, what is the most important driving factor? Well, it's this direction right here. And I might be able to say, actually, I can kind of ignore this direction right here. I can take this two-dimensional data and collapse it down to just this one dimension, just that one line. I could project everything onto that line. Okay, so you could project higher dimensional data onto this important line. And everything that's happening in this direction, that just might be noise. It might not be that important. Okay? So you could removing dimensions that are unimportant can help distill more important information. Okay? Here's another example of that. Let's do another plot. Let's just give you some data, okay? Here's some time data, and here is some position. Let's just say this is the position of our mass damper, our spring mass, S of T. Let's say we actually built this spring mass damper. This thing that we had that's zipping along right here, going boing, that's the position over time, okay? All right. Let's say we were measuring it, okay? And we were measuring its position with like a camera. And that camera is telling us it's there over time, right? And if we're looking at that data, it might look like this. Because while the whole thing is moving like this, there's noise in the measurement. The camera might not get the exact position right. Maybe certain pixels over to the left, certain pixels over to the right. This stuff here, that stuff is noise, right? That we don't really care about, right? Now, if you take a class in signals and systems, you would say, oh yeah, I know what to do with that. We would add a filter. If it's a frequency-based noise, we can add a frequency-based filter. It's high frequency stuff. We can say we want a low pass filter where only lets this low frequency stuff pass through, and this high frequency stuff is canceled out. That's what a low pass filter does. Or if we actually wanted to know what the noise was and didn't care about what was happening in this low stuff, we would do a high pass filter, which says, hey, only this high frequency noise stuff will stay. This low frequency noise stuff will go. So it'll end up looking like, it'll end up looking like, I don't know, like this, where all the low frequency stuff is gone. Okay. Low pass will give you this. High pass will give you this, right? Okay. That's a traditional way to do filtering, to filter out noise, okay? But there's a machine learning approach as well. It's using dimensional reduction. It's using this unsupervised method. Now, the reason it's an unsupervised method is because we're not trying to fit labels. All we're trying to do is to trying to find patterns in the data, right? For instance, this is just data, and we're asking, hey, what are the important patterns? And we're like, okay, that direction's super important. In fact, we can maybe ignore this direction. It doesn't matter, right? And here we look at this data and we say, you know what? This might be what's really important. All this stuff, all this little noise stuff, that might not matter. So there's another approach other than filtering and machine learning that's really good at taking noisy stuff where there's a lot of stuff that might not matter, but some that does, and leaves the stuff that does. It's called an autoencoder. And we'll see how far we get today. I'm not sure we'll have time. Oh, we can try. We can try to code up an autoencoder today. All right. Maybe we'll get to it. All right. So an autoencoder. All right. An autoencoder is a neural network that's job is to take an input and its output is itself. It encodes itself. All right. That's all it does. I mean, seriously, that's it. That's it. So, oh man, I'm not sure if we can code this up today, but in Keras, it's actually not too hard. Okay. But the idea, so an autoencoder is an unsupervised method of dimensional reduction that consists of an encoder and a decoder. Okay? Whose task is to encode an input and match it to itself. That's the idea. So imagine you have some input data, okay? Some input. This is through a neural network. Okay? So here's our inputs, all right? And it's going to go into some layer of a neural network that we'll call, this is going to be the encoder, okay? Okay? All right. So we can make this fully connected. You cannot make this fully connected. A dense layer, right? Okay. Then we're going to leave a space here. Where over here we're going to have another neural network layer. Okay? It can be a whole network if you want, not just a single layer. This is our decoder. Okay? And then it comes out to an output here. This is our input. This is our output. You can have as many inputs or outputs as you want, as long as it's the same number of hidden inputs and outputs. That's pretty important to the idea of an autoencoder. That's our output. Right? And in the middle, you're going to have some smaller layer. Okay. Okay. And we're going to connect this fully connected. This layer doesn't necessarily need to be fully connected. But I like drawing all the lines. Okay. You have some smaller layer in the middle. Okay. And that smaller layer is important. Okay. So the task you're going to give it is you're going to say, hey, here's my input, and I want to minimize the difference between my input and my output. I'm going to optimize all these weights and biases in all these layers. Okay. All right. So that way the goal is that the input equals the output. All right. So what is going on here? You're a whole neural network to say, hey, there's my input, and I want the output to be exactly the same. That's silly. What's all this for? That's crazy. But what it's useful for is dimensional reduction. You see, when we were doing our various in-class coding examples where we tried to get, let's say, try to fit a function with a neural network, right? Okay, we would try to fit that function as best as possible. We might even make this a really deep and wide neural network that we train for a long time. Okay, but it also has the capacity to overfit that signal. So if there's noise in your input, you know, a little noise that's in your input, right? There's stuff we'd rather get rid of. So when you have this middle layer right here, that's that's much smaller than these encoders and decoders, right? It puts all the information through a bottleneck. You can't put more information through this entire neural network than what we can make through this tiny layer right here. Okay, that layer is a bit of a bottleneck. So what this forces it to do is that when you are trying to train this neural network to capture the input and output to be the same, it's going to have to strip out information that's not that important in order to make so it has to kind of pick and choose when you're doing gradient descent what's going to encode into this layer, right? And what it tends to get rid of is noise. So when you have pictures that have fuzziness or blurriness or just general noise, right? What's one of the layers that people will put into their neural network? They will put an autoencoder right near the front, okay? Because this can denoise not only a little signal that looks like a sine wave with little squiggles on it, but like a picture with noise, right? Okay, so with the picture with noise, excuse me, you can so like all of a sudden it can say, hey, you know what? This thing that looks like Fozzie Bear, but it's got all these weird fluffies and other things on the outside, right? Let's get rid of all that extraneous information. This small layer in the middle, okay, which captures what we call like the latent space. All right, and we'll talk about latent space in just a moment here. It forces this small layer forces the network to simplify its representation of the image, and as a result, gets rid of things like noise. And by dimensional reduction, we say the dimensions that it has to represent the image in now has to be reduced to the number of inputs and outputs and weights and biases in and out of this smaller layer. So it's going to reduce the dimensionality of your representation with weights and biases. I mean, the weights and biases are a vector, right? You can put them all in a vector. So it forces the representation to be in a smaller vector. And so it can't be as complicated. And therefore gets rid of the noise. So it's crazy. That's what autoencoder is. It says, hey, let's make the input equal the output. And you can use the MSE loss function in that for all you, and then there you go, right? Okay, that's what an autoencoder does. Now, I was hoping we can see where we get on the auto. I'm worried we won't finish is the only thing today. I mean, we do want to capture stuff tomorrow. Well, maybe on Tuesday. So maybe we'll finish this up on Tuesday. We'll just get a little bit. We have enough time. No, not sure we do. I'm not sure we do. We might have to end a little bit early today, friends. I apologize. Oh man, I was hoping we get through more of this. Maybe we can talk a little bit more. But so anytime you have data coming in that you think is noisy or you want to find some representation of, right? You can put in a layer that is an autoencoder. Okay, pretty handy trick. Pretty handy trick. Okay, I think that really wraps it up for today. So I think that make sure that you're working on your projects, all right? And if you're doing image processing, you know, autoencoders can be good. You can also add a regularization term to your cost function, like we've done in the past. Anyway, but so I'll refrain from giving you more stuff here today. So instead, we're gonna do one last lecture on Tuesday, and we have our project workshop on Thursday. Okay, where I'll give you feedback on your projects. All right, folks, thanks so very much. Best of luck. Take care. I'll see you all soon.